The derivative is the gradient or the rate of change of a function. Now if you look at this graph here, you can see that the gradient of the curve is gradually increasing as we go along. So it's not constant at any point. So the gradient is different depending on the value of x, i.e. where you are on the graph. To find the derivative from first principles, I'm going to use our original formula for gradient. What I'm going to do is I'm going to choose another point further along the graph, which is h further along. So this is x plus h. That will give us a point here, and this value on the y-axis will be the function of x plus h. Now if I join these 2 points together with a straight line, we can calculate the gradient of that straight line. And it's actually not that different from the gradient at this point, where we have the value of x on the graph. So we're going to use the gradient of this line here between the 2 points as an approximation for the gradient at x. Now remembering our formula for calculating the gradient of a straight line, it's going to be rise over run. Now the rise in this case is the difference in the y values. So it's f of x plus h minus f of x. And the run is going to be the difference in the x values. So it's going to be x plus h minus x, which is simply h. So I can write down our formula for gradient being rise over run. So m is our symbol for gradient. Our rise is f of x plus h minus f of x, all divided by our run, which is h. If the value of h is made smaller, that's going to bring this point closer to our original point. And the smaller h is, the closer the point gets, and the closer the approximation to the gradient at x. So ideally, we want h to be 0, so that this point and this point effectively merge here, and what we're calculating is the gradient at x. So I'm going to rewrite my equation, but this time I'm going to call it f dash of x, which is, the dash means the gradient of the function of x, and it's at the limit as h approaches 0. And then the rest of the equation is the same. F of x plus h minus f of x, all divided by h. And this becomes our equation that we use in order to find the derivative from first principles. Now let's see how this works in practice. Let's take the parabola graph, where the function is the square of x. As you can see from this graph, the gradient is different at all points. Here in the center where x is 0, it's a horizontal line, the tangent to the graph, so we've got a gradient of 0. The tangent increases as we move to the right, so we've got a positive gradient, getting more positive. And over on the left side, you can see that it slopes down negatively, so we've actually got a negative gradient. So the gradient is different at all points on the graph depending whereabouts we are, so depending on our value of x. So what we do is we rewrite our equation for our derivative. That's still the limit as h approaches 0. But what it is, it's the function of this value. And the function is a square. So whatever your value on the x-axis is being squared. So in this case, the value is x plus h, and that is being squared. And then minus the function, just the value of x. So it's simply minus x squared, all divided by h. So the limit of h approaching 0 means we want to actually put in a value of 0 for h at some point. But here it's not possible because that would be putting 0 as the denominator of a fraction, which we can't do. That's a value that's undefined. So what I'm going to do is I'm going to take this bracket up here and I'm going to expand it. And that's going to become x squared plus 2xh plus h squared. That's the expanded bracket here. And then we've still got minus x squared. And it's still all over h. Now you can see we've got plus x squared minus x squared. So those two cancel each other. And what we now have is the limit as h approaches 0 of 2xh plus h squared divided by h. Now I can cancel h on the bottom with h in each term on the top. But I'm going to do it the safe way. I'm going to take h out as a factor on the top. And I suggest you always do this just to avoid making mistakes. So we take h out as a factor and we're left with 2x plus h divided by h. And now it's very clear that this h will cancel with that one. And what we're left with is the limit as h approaches 0 of 2x plus h. Now I can put in my value of h equaling 0. So what we get is our derivative of the function of x is 2x plus 0, which is just 2x. So that is our derivative from first principles. Now let's have a look and see how it actually applies to the graph over here. So our derivative we've worked out is equal to 2x. So our derivative, remember, is our gradient or our rate of change. Now, if x is equal to 2, what is the gradient at that point? What we do is we substitute 2 in for x, and we have got 2 times x, which is 2, which gives us a gradient of 4. What about at x equals 4? Again, we substitute 4 in for x, and we have got a gradient of 8. So as you can see, the graph is getting much steeper up here. What about at this point, when x is equal to 0? We have got a gradient 2 times 0 of 0, and that's what we expect. The tangent to the curve at that point is a horizontal line, and that has a gradient of 0. Let's just double check. At minus 2, we're expecting a negative gradient because it slopes downwards. So our gradient when x is equal to minus 2 is 2 times our x, which is minus 2, which gives us minus 4. So there we are. We can calculate the gradient of the graph at any point. And that is our derivative from first principles.